Today we will continue with factoring polynomials, but today we're going to look at two very special cases, a lot like what you see here. Okay, we have to remember back to some previous lessons when we had problems that looked like these, where we had to actually multiply our binomials together or square our binomials. Okay? And our answers were very interesting that when we had a problem like this, some people call it a plus b times a minus b. I just call it Bob. If you did it by multiplication or by FOIL, you would always get this number squared minus this number squared. When we squared a binomial, or we have a binomial squared, we would always get a perfect square trinomial. And notice that this is equal to 9h squared. The 144 is equal to 12 squared. This was a plus sign. And then this 216h is equal to 9h times 12 times 2. That's the way we worked these problems because they were special products and we got special answers. So now let's determine, are these 5 polynomials actually differences of 2 squares? Please press pause and decide what you think, and then press play again. Alrighty then, let's see. Number 1, 3, and 5 were differences of 2 squares. So let's see, here we're squaring x, here we're squaring 10, and we got a difference. This number 2 is not a difference of squares. This is a sum of squares. We want a difference of squares. Not only is a sum of squares not special, normally it can never be factored. The only way it can possibly be factored is if there happens to be a greatest common factor or some common factor that you can factor out. But most of these don't have it, so this is not factorable. Okay, number 3 is a difference of 2 squares. Right here we have 7g squared, and right here we have g squared. So we have the difference of 2 squares. Number 4 is not a difference of 2 squares, even though we have a difference, and this is something squared, but 8m squared is not anything squared, because the 8 is not a perfect square. Number 5 is a difference of squares. X to the 6th is x to the 3rd squared. Remember our power of power rule. And 36 is, of course, 6 squared. So it is a difference of squares. Okay, so now let's try to actually factor them. See if you can remember what we talked about, how to factor these, going backwards. Press pause, and then come back when you're ready. Okay, so number 1, I have a difference of 2 squares. So when I factor it, I'm going to get my answer looking like Bob. It's just going to be x plus 10 times x minus 10. Number 3, we had decided that we were squaring 7g squared and g, so my factored answer will be 7g squared plus g times 7g squared minus g. And the plus or minus can go first or last, it doesn't matter. For number 5, let's see. Here we're squaring x to the third, and here we're squaring 6. So our factored answer would be x to the third plus 6 times x to the third minus 6. Now remember, the other special case is perfect square trinomials. So I want you to take a look at all 7 of these and decide yes or no, are they actual perfect square trinomials based on the criteria I showed you a little while ago. Go ahead and press pause, decide yes or no, and then come back. So let's say our answers. Number 1, 3, and 7 are perfect square trinomials. Number 1, because here we're squaring x, here we're squaring 9, we have the plus sign that we have to have, and in the middle we have 9 times x times 2. Everything checks out. Number 2 is not, because let's see, right here we're squaring 5n, right here we're squaring 2, we have our plus sign, so far so good, but in the middle we need 5n times 2, that's 10n times 2. This would have had to have been a 20n, so it's not a perfect square trinomial. This one's a perfect square trinomial. Here we're squaring c, here we're squaring 5, we have our plus sign right here. In the middle we need c times 5, that's 5c times 2, we have our 10c, it's all good. It's okay for this to be a minus. Number 4, whoop, can't have a minus sign there, not for it to be a perfect square trinomial. Number 5, let's see, here, whoop, 10 is not a perfect square. I'll stop right there. Number 6, let's see, right here I'm squaring 10b to the third. Right here I'm squaring 6, so far so good. I've got my plus sign. 10b squared times 6, I'm sorry, 10b cubed is 60b cubed. So in the middle I need 2 times that, which I don't have. So it's not a perfect square trinomial. Number 7, here I'm squaring 6p to the fifth. Yes, that equals that. Here I'm squaring an 8. I've got my required plus sign. In the middle I need to have this times 8 times 2. That would be 48p to the fifth times 2 is 96p to the fifth. It's okay to have a minus sign here, so we're good to go. So now we're going to actually factor these ones, the 3 that are perfect square trinomials. Think about what I showed you before, press pause, and try to factor these. At any point in time, if you're catching on, you want to press pause and go back and try again, you may. So let's see, here we're squaring x, here we're squaring 9. We already verified this is a perfect square trinomial. I see a plus sign here, so I just get my binomial squared with this operation right here. If you work this out, you will get this. We know it's correct. Number 3, let's see, here we're squaring c, here we're squaring 5. We have a minus sign here, so it's just c minus 5 squared. Number 7, here we're squaring 6p to the fifth and 64, and we have a minus sign there, so it's simply 6p to the fifth minus 64 quantity squared. And we are good to go. Work this out the old way, you should get that. That way you know you did it right. Okay, so for these 7 polynomials, you want to determine, is it a difference of 2 squares? You can write a d next to it. Or perfect square trinomial, write a p. Or if it's nothing special, just write n. Press pause and come back. And here we go. Number 1 is a perfect square trinomial. It meets all the criteria. Number 3 is neither. Now, there might be some stuff we can do, but okay, it's definitely not a difference of 2 squares because it's a trinomial. It's not a perfect square trinomial. I don't see a perfect square right there. Okay, number 3 is nothing special. Number 3 is a sum of squares. There is absolutely nothing special about a sum of squares. And remember, usually you can't even do anything to a sum of squares unless there happens to be a common factor that you can factor out. Number 4 is the difference of two squares. We're squaring 25h, and we're squaring 3, so it's the difference of two squares. Number 5, okay, it's a trinomial, so the only thing special it could be is a perfect square trinomial. Can't have a minus on there for a perfect square trinomial, so it's not anything special. It might be factorable, I don't know. Number 6 is a trinomial, so the only thing possible would be a perfect square trinomial. I don't believe 2 is a perfect square, so we're moving on. And number 7, this is 10y to the 5th squared minus 1 squared. This is a difference of two squares. So now let's try to factor these three special ones. Press pause and come back when you're ready. Number 1, we would determine that it was a perfect square trinomial. So I'm now going to get a binomial squared. And I'm going to have a plus sign right here. What am I squaring here? 7x to the 3rd. What am I squaring here? 5. I'm done. It's that easy. Number 4, we realized that that was a difference of two squares. So when I factor it, I'm going to get my friend Bob. Put a plus sign here, minus sign here. Right here, I'm squaring 5h. Right here, I'm squaring 3. Repeat and rinse. Number 7, we also said was a difference of two squares. So I'm going to bob it. Here I'm squaring 10y to the 5th. Here I'm squaring 1. This is 10y to the 5th minus 1. I'm done. Once you know it's special, factoring it is so easy. Can anything be done with these other ones? Well, maybe. For example, for number 2, I see a common factor of, let's say, 6x squared. So I can factor out that 6x squared. Number 3, sum of squares. Number 5, I don't see a common factor. It's nothing special. We might be able to factor this by some of the other methods. I don't think it is factorable, but it's not unfactorable because it's not anything special. Okay, number 6, right away, I see I can factor out a 2 and get this. And this may or may not be factorable, but I was able to do some factoring. At first glance, these two problems do not look like they're any one of our two special cases, but they are. They absolutely are. Press pause and see if you can figure out why. While you were gone, I just happened to notice that number 1 has a common factor of 3. I'm going to go ahead and factor that 3 out, like the first factoring that we ever learned. Okay, now look what's inside the parentheses. This is a polynomial that is a difference of two squares. Here I'm squaring 2m. Here I'm squaring 3. So I can factor that. So we still have our 3 out front, and it's just going to be 2m plus 3 times 2m minus 3. Okay, number 2. I see a common factor. Do you? I see a 2k. So this equals 2k times k squared plus 20k plus 100. And this is a perfect square trinomial. It's equal to k plus 10 squared. And we still have our factor of 2k. So this would be the answer.